Chapter 5 Torsion Part B Example 1 in Parallel and Series Condition. If you remember this example, which we had already solved with a, a different approach, that's a aluminum post, mhm, which is reinforced with a brass core, mhm, handling a axial force of 9 kilopounds at the top. So that's a 9 kilopounds at the top, and a rigid cap, as we previously studied. This is example, acts like a distributor of force between the two material, the outer cylinder of aluminum and the inner core of brass. If we know the specification of the each material, which for modulus of elasticity for aluminum and brass is provided, we want to know the forces or stresses. So stress, if as soon as we know the forces, force over area is a stress. uh, let's see what we have here. So that's from the data. E of AL and E of BR is provided one within a KSI unit. Mhm. And the also dimension of inner and outer diameters is provided. If you remember, we had solved this in a solution one. If you didn't review this that video, I will provide the link for you at the end of this section. And this time, in solution one, we solved the problem with a far longer approach. We want to solve the problem with the concept of parallel and series, which again, if you don't watch the video of parallel and series concept, which make the problem solving of beams and shaft and this kind of configuration far easier. I will upload that for you as well. So let's see the solution one, which is a conventional method. First of all, we use equilibrium equation to see the free body diagram and forces. Then goes, if you remember, we created the compatibility of displacement for forces and deltas. And in the last, in the third step, we just write the load displacement, which is delta NL over EA for axial condition like here. And finally, after passing through all these three steps, we get the equation for the relation of which connects the force of aluminum by a relation to force of uh, brass. And by doing the mass, it and applying the previous equation, put it all together, it gives us the force of brass, which is it was 3 kilopounds, and force of aluminum, which is 6 kilopounds. And now this time, let's solve the problem in a far easier approach, which is a beams and shafts in parallel and series. So let's see how that works. If we call it solution 2, and we can easily see this is a parallel condition. Do you remember I told you the rigid cap acts like a force distributor of forces? So if two materials are uh, uh, bounded with each other and there is a force applied to them, there is no way to move at the same distance. So brass and aluminum has no way to move or to move down at the same amount of delta. Do you remember delta equal is a hint to parallel condition, and in parallel condition delta remains the same, force is distributed based on the stiffness of material. If we develop the equation for the parallel condition, force in each section is the stiffness of that material So that's we can over the total stiffness times the overall force, which is a inward push axial force of compressive force of 9 kilopounds. If you want to connect the dot, EA over L is axial stiffness, and for force of aluminum, definitely you need to go for aluminum if in numerator. And at the denominator, we have the total stiffness. And just by knowing this fact and developing this equation, likewise force of aluminum, no, just replacing the numeric value on force of aluminum, it just gives you a numeric value of what? A 0.599, almost 6 kilopounds. And doing the same step for brass gives you a 6 kilopounds for aluminum and a 3 kilopounds for brass. And if you compare this with the previous method, you can easily see it is just by a maybe two line versus a uh, developing three equations, then relate the equations, solve them simultaneously. So parallel condition, it solve the problem in a far easier approach. Thank you.